that much, maybe here and there, but like not really. The way it came to be was even early on in school, everybody kind of always thought like, oh, organic chemistry is this like difficult, hard thing, and I'm like, man, what's the deal? Like, what's so interesting about this? And so I decided to take it for fun and just to see what would happen, and I loved it. Like organic chemistry in particular is this weird concept where like it's too complicated for physics, right? Like you can't solve the 18 body equation of H2O with quantum mechanics and full solution. And so you come up with these like physics heuristics to follow the electron and what happens at the molecule level. But it's still small enough that it's actual like physics you're dealing with, and like that it's not like some totally unpredictable biological system that you can only think about statistically. And so it's this really cool world in between like what we can actually compute, but like it's a little bit too hard for that, but still close enough to like raw physics that you really have to kind of understand it. But no, at SpaceX I did not deal with fuel systems. The closest thing I did is I had a project as an intern to literally watch paint dry. And that's about as close as I came to chemistry.
Well, I gotta know more about that. Tell me, tell me about your internship. Literally watching paint dry.
Yeah. It was one of my intern projects, which I realized I need to pivot into something much more impressive if I want to get a real job. But we so at Vandenberg, we had a launch facility, and what we had to do is kind of guarantee for customers that there's sufficient EMI isolation for their sensitive satellites from everything else that's happening at the base. So you basically line the walls of the facility with a bunch of EMI kind of Faraday cage, effectively, that kind of prevents the signals from coming in and keeps a quiet electromagnetic environment. The other problem at Vandy's next to the ocean, which means it gets really humid. And it thermocycles a lot, which means that any kind of like coatings and paints and whatever else you use have the potential to like, peel and go bad over time. And so one of my manager at the time, he was trying to figure out like what the actual like kind of tiles and paint that we should use at Vandy, and was like, here, like thermocycle this and humidify it and see if it breaks. And so that was one of the great intern projects that I had to do, was sit there with find a thermal chamber and then sit there and watch paint dry.
Yeah, thermal chambers, they sound kind of fun at first, and then you get into the actual like implementation. I was doing some battery testing with thermal chambers, and it's like, this was cool for the first 15 minutes, but now it's just like I'm just in this room with pumps running and
Hey, you got a room. I was in a garage. Like,
okay,
only thermal
fair
chamber
enough.
I could find was a discarded one that nobody wanted, like in the parking lot on the third floor of Hawthorne. That was it.
Well, many famous startups have started in garages. How did you get into the world of Quilter and PCB design? And can you tell me kind of the origin story of how all that began?
Yeah, so the initial spark, came pretty early on at SpaceX, although I didn't quite think about tackling it just yet, right? So, I mean, in my undergrad, I learned a bunch about, circuit schematics, electronics. I had a passion project at the time where I wanted to make a RF distance sensor, like a millimeter accuracy point-to-point tag, basically, kind of what ultra-wideband became, but didn't exist at the time. So the only course I actually took in undergrad for electrical engineering was a microwave course. Which is really fun, get to build, some RF systems and drive this project home. And at SpaceX, one of the first projects I had to do was like take a part of the Falcon 9 power system and convert it into a soft start switch that we could use for EMI testing. Right, so when you do qualification for flight electronics, you do a whole bunch of tests to make sure that like things are compatible and they work, and this is the MIL standard 461 for those who know about that. I built this board that used the Falcon 9 power switch to kind of fit into the system, to be more flight-like during testing. And that was the first time I ever did layout, right? And like as I started doing layout, I opened up Altium, like, okay, learning this as an intern. I'm like, oh man, I better go fast because like I want to get a job here. This is cool. And it took me a long time to like figure out how to drive it, how to route stuff, how to whatever. I thought about like, why am I doing this manually? Like, why isn't there just like a button? And like, I've already have the schematic. Like, why do I need to express all this? I clicked the auto route button and understood why pretty quickly. And so abandoned that idea. Drove the board home, ended up reviewing it with a whole bunch of senior engineers, like asking for their help, like, please make sure I didn't screw this up. And then after I made the board, literally the first thing it did is catch fire in my hands. I made a nice, good schematic error where I didn't realize that the very thing I was testing for in terms of over voltage would then apply to the power circuitry on my own switch, and so I ended up frying voltage regulators. Pretty embarrassing classic mistake. That spawned my love for electronics, let's say.
Yeah, I mean, I wouldn't say only embarrassing probably for you in the moment, but in retrospect, I think you must. How do you look back on it now? How do you feel about that moment when you smelled the smoke and saw the flame?
I mean, I'm really glad I didn't set off the fire alarm. Let's start with that. That would have been a lot worse. You know, and I mean, in retrospect, like, I got the job, so okay, good. That worked out well. And now it's just a funny story. So obviously it's a fond memory. But, like, it's really illustrative of, like, you know, you jump in and you try to build something, and, like, there's just so much to know and understand about the physics of boards, and none of which is that intuitive, none of which is plainly written down in a single text you can read and just understand. A lot of which comes from, you know, tribal knowledge and experience and talking to people, and even those senior engineers who know a bunch don't catch everything, right, as they didn't in this case. So it's an illustrative case for, like, exactly the kind of difficulty of making hardware that kept coming up for us in SpaceX all over the place, obviously, right? This isn't the only case, and the thing that's driving me to try to help it.
So tribal knowledge is such a kind of a core tenet and a core operating principle of the layout engineering, you know, realm. How do you start to try to capture that? Because sometimes just having a set of existing PCB designs is maybe not enough to really understand what's happening underneath. Can you talk about kind of the culture of tribal knowledge and layout and how that experience has influenced how you build Quilter?
Yeah, for sure, for sure. So I have strong opinions in this. So I'll take you on a little bit of a tour here. So the first thing I like to think about is like, what is the job of a PCB, right? So, like, okay, we've got the schematic, we've got the PCB layout. The schematic is obviously an expression of our logic, right? Like, what are our inputs? What are our outputs? What is the function we're doing in the middle? And we need to express that somehow, so we draw a schematic. Or maybe if you design FPGAs, then you write Verilog, you know, or maybe, you know, there's some software tools that you can use. But at the end of the day, you draw a schematic. Then what is the job of the actual PCB design, right? In my opinion, simply stated, the job of the PCB design is to faithfully implement the intent of the schematic, right? Like, in reality, the only thing that an actual kind of PCB layout and design can do is either get the schematic right or screw it up. In a very, very coarse sense, those are the two options, right? And all of the kind of tribal knowledge, all the experience that people build up over years is a heuristic and an intuition around how not to screw it up, right? You're applying your experience to say, okay, if you do this, you're going to have yield problems. If you do this, you're going to have manufacturing problems. If you do this, the fab's going to push back and you're going to wait 3 weeks instead of 1. If you do this, it's going to be expensive. If you do this, you're going to have crosstalk and you're going to have a bad day on bring up. Like, if you do this, you're going to burn your chip, and like so on and so forth, right? But at the end of the day, like, we kind of learn those things from experience, from other engineers, from previous examples, from data sheets, from application notes, like these kinds of sources. But at the end of the day, like, one of my beliefs is that ultimately this is computable, right? Like, ultimately you can quantify, like, what is the manufacturing process, what are the thermodynamics happening on the board, and what are the electromagnetics from, like, a Maxwell equations perspective that are happening on the board. And it is possible to enumerate all of those concerns, create a threshold at which the circuit works or it doesn't, and to compute the answer to whether or not you're past the threshold or not. Now, in reality, that's really hard, right? Like, guess how many times at SpaceX we'd, like, design a board and, like, open up HFSS and simulate every trace and every crosstalk problem and, like, consider absolutely everything and, like, no, that's not what happens, right? Like, you design it, you're out of time, Elon's already yelling at you, you build it, and you hope it works. and you turn around quick when it doesn't, right? That's the reality. But that's why I think that tribal knowledge and that intuition and experience exists, right? Because, like, the best tool we have to quickly get through the design is to draw it correctly on the first go based on your experience, go through bring up and hope to God it works, right? And this is something that I want to change about this industry, right? Like I want to get us to a point where we have the sufficient tooling to actually quantify the full problem and to talk about it from a quantitative perspective of like, what is actually the crosstalk? It's never zero, but is it sufficiently below the threshold, right? That's the question.
I think a lot in this space about that threshold concept that you bring up is how good is good enough? And what I see a lot is there's kind of this move towards purism in this space where, oh, you could have saved a centimeter of board space there. You could have traced this, trace a little bit differently or done this return path a little bit differently. But in the real world, when, we actually have to get something shipped, the purism holds us back a little bit, and we have to find that threshold of what is good enough. Can you talk a little more about like how do you actually define that, and how do people define that for themselves in their own boards?
Yeah, it's a good question. So the reality is it's really hard, right? Like at the end of the day, if you've got, I don't know, like an Ethernet line and you're looking at the RX and TX side and you're worried about potential crosstalk there or something like that, right? Like what's easier? Actually going into the spec, figuring out the point at which your noise actually introduces a bit flip and a problem, figuring out the exact separation required based on the field equations, and then like computing it down to the T, or just saying, I'm gonna put them as far apart as I can and it'll be fine. Right? Like that latter one is the approach. And so I think like very understandably, every designer looks at their board and just says, I'm going to make this as best as I possibly can. And it's probably going to be good enough. Right? Or I have very high confidence that it'll be good enough. Right? And what that really is just a shortcut for the fact that like to actually compute that answer would take a lot of time, would take a lot of tools. Right? And so how do we approach that over time? Right? We have to automate it. That's the simple answer, right? The simple answer is we have to create automation systems that understand the schematic, right? Understand that like, hey, this line in the schematic is not just a line segment. It's representing a differential pair at 100 ohm differential impedance that's going to run at this power level and so on and so on and so forth, all of those specs, and understands that it's carrying specifically an Ethernet signal with that specific protocol, with that specific noise tolerance and so on and so forth. So that's step one, is just collect that information, right?
And that's an insane amount of metadata just on a little strip of copper, on a little strip of fiberglass. Is like, there's a lot of context there.
Yeah, and if you think about it, like that context is not in our CAD tools, right? Like if you open up a schematic file, the context isn't there. If you open up a board file, the context isn't there. Like at best, it's in the data sheet or in your head.
So you have all this kind of metadata context for what this trace or this design is trying to do. What's step two?
Yeah, so from there, now that you have the context of like, okay, we have a sensitive signal that's carrying some sort of, whatever, Ethernet transmission or something like that, then we have other signals that are going to be interfering, like a noise signal, a switching power converter or something like that. Again, you need to understand that between those two pins, between the inductor and the switching converter, you have high power and it's switching at this frequency with this, rise time and all of those kinds of things. Okay, so now that we have that context, then we can ask the question of like, what can go wrong, right? And the obvious thing we're hinting at here is crosstalk, right? And so then the question becomes, well, is it a problem or not, right? And you kind of have a few different ways to potentially simulate this, right? The first option, what humans do today, is just like, don't simulate it, just make sure that it's as far apart as you can, and chances are you're fine, which works 99% of the time, right? In most cases. The next one is to use a heuristic, right? So something like the 3 widths rule is a good example where, okay, 3 widths rule is really conservative. It's well known in the industry. If you're more than 3 widths apart, you're probably fine. And so if you set that as a design rule, you'll probably be okay. Short of some really crazy cases. The final answer would be to actually run a proper EM sim. Right? So to either do a quasi-static approximation, so compute parasitic capacitance, parasitic mutual inductance, things of that nature, or actually solve the time domain Maxwell equations and like do a proper S21 between the two traces, right? And so at that point, if you have the context of like, what is the offending signal, what is the sensitive trace, what is the S21, and take that transfer function and apply it and see if it goes above your noise floor, above your requirements or whatever, then you have your answer to, is this good enough or not, right? And the only way for us to really reliably start to do this as engineers is to automate all of this, right? It's to just have our context at our fingertips in our CAD tools. It's to make it a button click to do this kind of simulation. And ideally, for us, the idea is to take that a step further, close the loop, and train systems that get really good at satisfying all of those constraints.
So you don't necessarily have to run EM sims every time. You basically have to say, here's what it looks like when I run an EM sim on these types of structures. And that's where the machine learning AI algorithms come in and saying, oh, this looks like that. So, avoid this or do X, Y, or Z. Is that
generally
fair?
Yes? Yeah. Generally, yes. So there's a couple of different ways that you can sidestep this, right? So, for Quilter, like our simple goal long term, simply said but not simply done, is to automate all of layout, right? That's the dream, right? And to do that, we believe that we have to get the physics right, which means we have to capture that context, we have to understand the schematic, we have to be able to do all the physics, and then most importantly, we have to create something that creates designs that reliably pass all those checks, right? And that's something is where neural networks start to be helpful, right? So there's two ways to kind of approach this, right? So naively, if I had an infinitely fast computer, like this would be a trivial problem. I would just simultaneously look at every single possible PCB design, simultaneously run every possible simulation on it, and just pick the best one, and we're done, right? Easy. Of course, that's nowhere near the reality, right? Like we have very, very finite compute. It takes a long time to run these sims, and so we have to work around that, right? That's the only reason that we have to go and rely on things like neural nets. If I didn't have to use them, I wouldn't, right? So the next thing then is, okay, like the fact that these simulations do take a long time, how do we sidestep that? One easy way to do it is when you can afford to be conservative, use simpler simulations, right? So when you can afford to simply say, hey, the 3 widths rule is conservative, let's just use it. It's simple geometry, it's fast, right? Do that. Or the next step would be, in my opinion, quasi-static approximations, right? If you factor time out of the Maxwell equations, you just reduce it to parasitic capacitance, which for low enough frequencies is fine, right? This is what most of chip design does. And so that's kind of the next level. And then the final level, if you're really trying to squeeze margin out and you're really at the threshold of like, what is the closest we can get these things while still succeeding, when you're trying to beat humans, right? Do better than humans can on like density and whatever else. That's when I think you have to go all the way to a full wave Maxwell equation. So that's one thing you can do, is use simpler simulations when you have the margin, recognize when you're close to the margin, and then upgrade your simulation. The second thing you can do is, as you alluded, use the net, right? So I think of neural networks for my kind of functional purpose as a software engineer as an interpolative database. Right? So what a neural network can do is it can go and gather a whole bunch of examples and store them effectively, just like a database. Okay, that's not that useful. Like we can do that with a regular database. But what it can do then that's special is it can interpolate between those points. So we can simulate 1,000 geometries, pick one that's somewhere between a few of them, and then use the net to kind of interpolate, right? And they're really surprisingly good at that. They're so good at that that they can mimic human language and pass the Turing test. Like that's a shocking thing. So that's the second way that you can kind of accelerate these sims. You wouldn't ultimately completely get rid of them, right? Because at the end of the day, the net can hallucinate. You might be in an extrapolation region, which is really what human hallucination is. And to verify that, you'd want to run the actual sim. But you don't have to run it billions of times as you go through your design. You just run it at the end for the thing you think will pass it, right?
No, that makes a lot of sense. So avoiding extrapolation. So if I have point A and point B, I don't want to go all the way out to point C because that's where things get wonky. But if I'm between A and B, it's probably going to be pretty good, and we can verify that end product through the EM sims and make sure it does what we want it to do.
Exactly right.
Going back to the thresholds conversation a little bit, I want to play historian for another moment. Was there a threshold point for you where you said, I'm going to quit my day job, or maybe my day job ended and now it's time to start this new thing? What was that woke up one morning, you're like, today's the day, or what did that threshold look like for you?
Yeah, so my story was a little bit weird compared to most that start a company. So I'd always wanted to be an entrepreneur and start a company, but like I thought you'd have to be an adult first. I thought you had to like invent something first and have
I
it work.
feel that deeply.
Yeah, I was wrong about both of those, to be honest. But I didn't realize that. So for those of you watching who are young and ambitious, like, go start a company, don't wait. That's mistake number one. What happened in my case is I had left SpaceX just because I spent some good time there. I wanted to try some different things. Went over to a different company and for a few months. And while I was there, I was doing contracts. And one of the contracts I did for someone was actually an investor, where I helped them do some due diligence for another kind of hardware company. And after a couple of weeks of working with this investor, he turned around and said, "How would you like to start a company? I'll give you $1 million. Go for it." And I was like, "What?
Wow.
Okay, let's do it."
That's wild.
I always known I wanted to do it, but I didn't quite go and just take that step myself. Like, somebody came up to me and was like, "Hey, like, I believe in you. You can do this. Like, go solve a thing." And so obviously, yeah, I'm definitely doing that. That's a great deal. When I actually first started the company, I actually didn't approach PCB design, right? Like, our initial first idea was like, hey, we should make low-cost sensors for manufacturing context or something like that, right? Which turned out to be a bad idea for a bunch of reasons. And then I had proceeded to have like 10 other bad ideas. But I knew that, like, you have to validate the problem first before you spend all that money and time doing it. So the money was on Hibernate. I was, on my own, or I had one other person with me, and like, we were just trying to figure out like what actually makes sense. And after some amount of time, I basically just said to myself, like, I should be solving something that I understand really well. Right? Like, something that I know is a real problem that I've lived, where I can build the product for myself. And this was it, right? This was the obvious one. When thinking back to my time at SpaceX, for the, I don't know, thousands of boards that we designed over the time that I was there, like, all the different challenges, like, that's an obvious problem, a hard problem, but an obvious problem.
Yeah, I mean, even the shirt with Chris Gemmell, like the never trust the auto router, sort of mantra is very much a thing in the space. What do you see as the largest challenge or obstacle to overcome from a traditional perspective, and how did that influence your trajectory as you started to build this thing?
Yeah, that's a great question. So I spent a lot of time thinking about, like, why don't people use the auto router? Right? What exactly is wrong with it? And if you think about it from first principles, like, there's actually a really interesting analogy here to the software world, where the complementary statement is equally ridiculous, right? So what I like to think about by analogy is that a schematic is kind of like writing code, and a PCB layout is kind of like compiling your code. Right? Like, you're taking an actual well-defined spec of like the inputs, outputs, and function in the middle, and you're making it real, right? And in software, that's translation from a high-level language like C or Rust or whatever into machine code and targeted at whichever processor. And in our world, it's a schematic that then gets expressed as some combination of copper and fiberglass and silk that then again implements that, right? And if you think about it, like, okay, in the world of software, actually, compilers didn't used to exist, right? Like, you used to have to be an expert to write machine code, to do punch cards. You basically had to be a PhD level mathematician to make any progress. And like, when compilers started to happen in the 60s, 70s, like, people thought that they weren't going to work. Like, they make machine code that's 10x too slow, it's incorrect, like, this will never, like, it's not as smart as me, I'm a human, and like, all that stuff, right? And now I talk to a software engineer, I'm like, when was the last time you looked at the machine code coming out of your compiler? And they laugh. Right?
Never.
It's a laughable thought, right? Like, unless you're doing some really crazy, super high reliability situation where you have to understand the instructions, okay, like, but like 99.9999%, it doesn't happen. And I believe that compiler is what caused us to have the software revolution, right? Like, it is the reason that an operating system exists, that ChatGPT exists, that video games exist, that Riverside here exists. Like, all of these programs, the browser, like, they would be impossible if we were writing machine code. Completely impossible, right? But like, that analogy is exactly the opposite in our world, where if I told you, like, trust the auto router and don't check your layout, you equally laugh at me. Like, that's an equally laughable thought. And yet, like, the same revolution that happened in software, I think, will happen in hardware if we solve that problem. Okay, so then the question becomes, like, all right, what are the properties of a compiler that, like, were necessary to unleash this in software? The first property is that the compiler tackles the whole job, right? It doesn't compile like some fraction of your code and ignore some other fraction, and then you have to like mesh it together with something else, right? The second is that whatever fraction of the work it tackles, it completes. It doesn't tell you like, oh, I got to 98% completion. There's 2% of your code you have to go convert into machine code. The third thing is you can trust it, right? Like it is in some cases provably correct. And so you know for a fact that it will faithfully implement the intent of your code without having to check it. Okay, so those three properties have to exist for us in electronics, right? So the first is that autorouters, in my opinion, don't tackle the whole job, right? They don't tackle stack up. They don't tackle material selection. They don't tackle placement. They don't tackle floor planning. They don't generate pores. Okay, that's like problem number one. They just don't tackle the whole scope. And those impact the routing, right? Like your stack up choice, your placement are like the most important decisions in how the board's going to get routed. And you didn't even look at them, right? That's problem number one.
This is the context conversation again, but it maybe in a broader scope is not only is this trace running on PCA, running a Ethernet thing, and you got to make sure it's, twisted pair, whatever, like actual, how thick is that layer of fiberglass? How thick is that copper? That all plays into layout. That's additional context beyond, here's a little copper spot on the board.
Right. And oftentimes, like, okay, you can't fit this differential pair because it has to space out really wide and has really thick traces. Hey, if we make the dielectric thinner, or if we change the dielectric property of the material, boom, it's smaller. Now everything fits and we can fan out of our BGA or whatever.
And at the same time, here's what's in the range of manufacturable without going into special order, layup configurations 100%. Or something like that.
100%. Yeah, critical. So that's one thing, right? We have to increase the scope. The second thing is that auto routers are notorious for like completing 90% of the board and proudly saying, look, I did it. And if you've ever tried to clean up after an auto router, what you realize, which I don't wish upon anyone, not even my worst enemy, what you end up finding is that like it blocked off everything, which is why it couldn't finish the last 10%, right? This problem gets exponentially harder, where the first trace is trivial. The last trace, how did you make sure you left room for it, right? That part's hard. And so what do? You end up deleting half of what the auto router did to then reroute the stuff it didn't do, to then reroute what you just deleted. What's the point? Just start from scratch, right?
It's almost like, hey, we built 90% of a skyscraper, but we messed up the foundation. So if you could just finish up that top 10%, we'll be good to go, right? But like ultimately, we got to tear it down and start over because bad assumptions from the get-go.
I love that. That's a great way to put it. I think that's exactly right. And then the third thing, and I think the thing that auto routers are most infamous for, right, is that they don't understand the physics. That even if you connect everything, and even if it's manufacturable, and even if your DRCs pass, your port still probably doesn't work, right? And because the context just isn't there to get the physics right. There's no proof, there's no simulation, so on and so forth. So how do we get to a compiler for electronics? How do we get to the point where you feed in a schematic, you fit in the board outline, place your components, click a button, and don't even review the layout? You have to tackle the whole problem, you have to complete it, and you have to guarantee from a physics perspective that everything checks out, that the board faithfully implements the intent of the schematic, right? And so I think that you have to tackle all of that. And this is really what Quilter's built around, right? Like we consider that whole problem in our scope. We think that the best way to do this over time is to do it at first for small boards, then bigger boards, then bigger boards, then bigger boards. But the whole way through, tackle the whole problem, get to 100%, hold ourselves to the level of proof of showing all of the validation results, and then just growing the complexity that we can tackle over time.
I love the idea of, just for most things, the idea of baby steps and building up from something that is tackleable and manageable into larger, more complex systems. And that's where, like, on the simple systems, maybe we can do it in machine language, assembly code, but as it gets more complex, like, the idea that someone could tell me how, the machine language that's running through my GPU right now is like no way, that no one's going to be able to do that.
Right.
So can you kind of set the scene for us then? So you've talked a lot about there's kind of an implied schematic input into Quilter. Where are the boundaries of Quilter? Does it replace my existing PCB design tools? Is it kind of a agent that helps me out? What's the scope and where are the lines drawn today?
Yeah, it's a good question. So Quilter, like, we're built very much with enterprises in mind. And this is primarily because, hey, I'm building for myself when I was at SpaceX, right? Like, what was the tool that I wished I had, right? And, like, the idea that I could go to the whole company and say, hey, guys, stop using Altium. Like, use something else. Good luck.
Right.
Good luck.
Yeah.
And this is true at any company, right? Like
Zero
this is
chance.
true at every single company. Like ripping out a CAD system where you have all that. Like I know a couple companies that are trying to go through that, and like, oh man, that's a decade-long project, and you have to convince people, and yeah, very very difficult.
And by
So
the
I don't
time
think
you
that
get
makes
it
sense.
done, maybe that was the wrong design choice, and the world has changed.
Exactly. So I don't think that's the right thing. So we very intentionally work directly with the existing CAD systems, right? So because we're not really competing with the CAD systems, we're competing with the layout labor happening inside of them, right? So the basic workflow for us is okay. I've opened up Altium, I've drawn my schematic. That part doesn't change. I then start creating the constraints of my board. So my board has an outline. I have certain connectors that want to be in certain spots. I have certain, keep outs. Maybe I have a room for components that are tall that have to fit somewhere into my enclosure, those kinds of things, right? And then otherwise, all my components stay off the board. I don't define the rules. I don't define the stack up, none of that. We take those and we upload those into Quilter, and then Quilter will take you through a conversation about the schematic, right? We have this system that we call circuit comprehension, where we attempt to identify what is effectively happening on all the pins on your board, right? And this is fundamentally where our biggest kind of work and limitations are, is like there's things we can understand today and there's things that we can't, right? So we can understand where you have a differential pair that needs impedance control, or a single-ended impedance control trace, or a switching converter where you need to minimize your return loop and whatnot. But like as an example of something that we don't understand is like high voltage, right? Like if you have a 400 volt requirement, we're not going to correctly separate that, and like that's not going to be a good day, right? So the fact that we didn't discuss that in circuit comprehension is your clue to know, hey, Quilter doesn't understand this, so I shouldn't rely on it to solve that problem for me, right? So we're very very explicit about like the kinds of physics we can tackle today and the kinds that we can't. Then you pass that off into the reinforcement learning system. It runs, generates a whole bunch of candidates, so on and so forth, picks out the best ones, grades them, and shows them to you in a report, right? So you can look at like, okay, what does this board look like when I do it in 4 layers, or in 6, or in 8? What happens if I require 10 mil trace in space versus 3? What happens if I have, a signal ground stack up, a signal ground signal stack up versus signal ground power stack up? And like, are those good choices and whatnot? And so you trade between those, and for each of those candidates, you get a report that says, here's the completion we hit, hopefully 100. That's what we hold ourselves to. And then here's all of the physics checks for all the signals you told us about, right? Like, did we properly couple the differential pairs? Did we pass over a ground split? Did we make the high current traces wide enough? Did we do pores for them and make them wide enough? So on and so on and so forth. And anywhere that we didn't, you'll see that. You download the board file and you're back in Altium, right? And that part I think is critical, because today we're not at the point where we're telling you, trust me, bro. Like, no, like,
It's not here's the Gerbers. It's put it back in the KiCad. Okay. Yeah.
No, exactly. Yeah. I wish we could go straight to Gerbers, right? That would make my life easier. But the reality is that you still got to review. You still got to modify things. It's still doing silly things now and again. And it'll be a while before it really is just trust me and go to Gerbers. And so that's kind of how it works. It integrates with the existing CAD systems for that reason.
So it sounds like you've come a long way, but there's still a long way to grow and a long way to go. What has been the response to layout engineers who have tried this tool today? Any stories you can share of times that it really got it right or times that it really got it wrong?
Oh yeah, definitely both. Both definitely still happen, right? And it's very much about like, are you in the scope of what Quilter can do, right? And to set the context for scope, I'll give you just a couple of concrete examples, right? So when we first started out, to be honest, when we first started out 4 or 5 years ago, I spent a couple of years just trying to think about like, how do we even approach this, right? Like, the initial idea was, hey, place and route works within chips and FPGAs. Could we just use that and solve the same problem? Answer turns out to be no, but it took me 2 years to figure that out, unfortunately. When we started coming up with our own ways, we could start to do really simple boards. So I'll give an example of like one of our early kind of hobby users built something like this, a little automotive board, ESP32, a couple components, ODB connector, easy stuff, right? Like, so we could do this pretty early on, and that's no problem. What we've been tackling now in terms of a reach goal for us, that by the time this airs, I hope we will have published and talked about, and if not, it'll be closely thereafter, something more along these lines. right? So at this point, we're trying to tackle like entire single board computers, right? So in this case, this is a NXP IMX8 processor, DDR4 memory, Ethernet, Bluetooth, Wi-Fi. This board is about 1,000 components, 5,000 pins. We're doing a different variant of it where we have a separate SOM and a separate baseboard so that we can tackle them independently and just like test it out that way. But like, we're not quite at the point where this is easy, but we are at the point where this is possible.
Yeah, that's a big board. That's like a legit enterprise grade system you might pull out of any sort of device around here.
Yeah, 100%, 100%. And so in that realm, it depends where you are, right? Like today, if you go and you throw this into Quilter, like you'll get some good chuckles, right? Like it's bleeding edge for us for a reason. We're just barely to the point where this is becoming possible today. And hopefully in a couple of years, this will be bread and butter, right? Maybe sooner. But if you throw in something like this, like obviously, like by now this is trivial for us, right? And so where we found kind of the most traction with real companies, real enterprises, real customers that use this today is primarily in test engineering. So it's not at the point yet where you like want to design a 1,000,000 unit production run board that's going to be used in high reliability and is super optimized for cost. Like humans still do that better and will for a while. But if you're making a test board or a test jig, or you're an aerospace company and you're putting electronics into radiation environments, or you're making something to exercise in hardware in the loop tests, or you're doing a first prototype just so you can give the firmware engineers something to write code on while the designers work on the final product, that's where it makes sense. And so we're routinely taking boards from these companies that take people even 2 or 3 weeks to design by hand and compressing it to, a couple hours of Quilter runtime plus maybe an hour of cleanup. And that's roughly where this board will be by the time hopefully this airs. Is Quilter does most of the work. You do maybe a half day of cleanup or so, and you fab it, and we will fab it, and we'll get it to work.
That's pretty significant. I never thought about. I think in the world of PCBs, you always think about the production run, where like every little bit matters, and you're trying to squeeze every bit of performance and cost, performance out of it and costs away from it. But there's so much circuit design that goes into kind of 1-off or 10-off, or just, like you said, that test or hardware in the loop sorts of systems. Being able to do that where you don't necessarily care about getting every drop of juice out of it, you just care about getting something that works. Your thresholds are maybe different in this case.
That's right. Like you're going to make 3, not 3 million of them. Right? It's okay if they're a little more expensive. There's a lot of things where it's okay. What really matters is that you have them today, not 2 weeks from now. And in reality, from my experience at SpaceX, like for every one board we flew, we probably had a dozen that we didn't. Right, like sub-circuit tests, qualifications, thermal cycles, radiation tests, HIDL, test equipment, test rigs, jigs, like interconnect boards, spoofing boards. I mean, you name it, right? Like, it's just like code, right? You don't just like write a whole website and like ship it into production YOLO, right? Like, you write little tests, you build it up over time, you do local development. Like, it's the same thing for us, and that's where the cost of the board and the criticality of the board is lower, but the time is the same. And the time to market saved in that step is just as valuable as time to market on the final design.
Yeah, and that's where kind of maybe the purism comes in a little bit. And the engineer in all of us wants to make the best possible perfect thing, but the reality is timelines and design constraints mean, like for this, like it'd be much better to be in person, but this is the only way we get to have this conversation. And that's it's great that we get to do this. Where do you run into the most pushback with this, and what sort of skepticism do you see, and then how do they respond when they actually kind of get the full picture of what you're trying to do?
Yeah, it's a good question. I think there's kind of 2 stages of this, right? Like, initially when people hear about like, oh, AI and PCB design, like initial response is like, oh, it's a joke. Like people don't understand my space. It's so hard. Like, and like, I don't fault people for thinking that way. Like if you go to ChatGPT and ask it to draw a layout, like you could get some really good laughs, right? And it makes sense to me that for a lot of people, the perception is that like AI is synonymous with a large language model. Large language models understandably don't know the first thing about electromagnetics and physics and how to design a board properly. And so if you think that's what it is, of course you're going to conclude that it's a joke and it's really, really far away from doing anything. what ends up happening with us is that when I talk to a company, and like do a demo basically, and like talk about all this reasoning and how we're approaching it, usually something clicks and they're like, this makes sense, right? This is like first principles thinking. It has the potential to eventually work. And the conversation switches from what are you even talking about to can this do my boards, right? That's really the design. And the way we think about this is like, if you have boards that Quilter is capable of doing, Quilter should just do it, right? Because it's going to be faster, the board will work, and you can move on to the harder board. But there's plenty of boards where Quilter cannot do it yet. And so for those, go save your time and go work on those ones, right? I'll give you the most extreme example of this was a conversation I had with Jensen at NVIDIA. And he's like, I love the idea. We're using reinforcement learning on chips all the time. This is so great. Can you solve my DGX workstation with 8 GPUs and 500,000 pins?
Yeah, no.
Not yet.
I mean, that's a... I won't.
Yeah.
I won't get into server board design. That is a whole thing. Yeah.
That's a whole thing, right? And so I think that's really the discussion we have in the professional context is like, does your team work on the kinds of boards that are applicable? And if you work on server design, sorry, like not yet. We're not for you. Not yet. We'll come back to you. But if you work on test boards, if you work on even things of this complexity, like let's talk. We might be there.
So let's look at the future a little bit. Where do you see this going both in the short term and where do you see this in like maybe 10 years?
I mean, short term, I think our direction is very straightforward, right? It's increase the capability of this thing to solve more and more complex designs, right? By far the hardest part of this is like, I've got a dense BGA with a ton of routing. All this physics introduces constraints and makes it harder. I've got a lot of components. It takes a lot of compute. And there's a fundamental kind of geometry solver that lives underneath all of that like tries to reconcile all these constraints and all these optimizations. And we're just going to keep investing as much as we can into that, right? Adding constraints, adding more physics simulations, investing in the ability of the solver, and jumping from, obviously we've jumped from this to now hopefully this. Next step is to make this easy and make it to the point where this would pass a human design review, right? I think that's for me the next kind of milestone is like the output we'll produce and we'll share our outputs publicly at some point for a board of this complexity. Like they would never pass a design review, right? There'd be so many issues that people would flag that like it'll work, but it won't pass the design review. So that's the next level. It's like, hey, if you actually put this in front of a serious set of engineers who's doing a real design review, how do we pass that? And that's kind of the short term for us. And of course, eventually getting to those server motherboards.
When I think about AI, I see there's kind of this like from 0 to 1 gap where we had nothing and now we have something that's, like a first or second generation model. And then from there, like that was a huge part of getting the thing going, but to get it into, from something that's good to something that's great or indistinguishably great is maybe a greater challenge, but a like smaller progress from a like outside perspective. How do you see, those first steps, the difficulty of those first steps, how do they compare to the difficulty of like the 9th and 10th step?
I mean, to be honest, they're both hard, right? Like it's just the reality that like even thinking of how to approach a problem like this is really hard. And even when you've figured it out, you're probably going to delete your whole approach and redo it a few times. It's research at the end of the day. And it's hard because it's unpredictable, right? And we accommodate for that. So I think that like that was definitely the biggest challenge of the early days. It's like, let's look at the prior art. Let's look at all the papers for existing routers and how they work and figure out what went wrong with them. And then now what do we need to introduce? How do we solve those previous problems to even start to approach this problem? Once you have something to build on top of, at least then you have a proof by existence of like, hey, this just barely works, but we can optimize it and make it better. And you can start to break that apart into engineering problems of like, hey, the way that we represent this part of the circuit board, the BGA, is really silly, and that's stopping us from being able to do good fan outs, right? Okay, let's re-architect, let's understand what exactly do we need to capture about that BGA. Can we simplify that part of the problem, eliminate complexity, and approach it? And those are pieces you can break apart. And my personal way of kind of breaking these problems apart and making them approachable, right? It's certainly not to just say, hey, let's go from this to a server motherboard all in one go, right? Like that's just, we're going to spin and never get anywhere. So what we try to do is we try to find kind of the intelligent next type of board that makes sense, right? So I'll give you an example. Like one of the discussions that we're currently having with a number of potential customers and current customers is whether it makes sense for Quilter to tackle flex designs, like flex boards.
Sure.
And It's an interesting case because like it's mostly a routing problem. It's far from the hardest routing problem. And on the surface, I kind of thought that maybe it's not that valuable because you can do it pretty quickly. But what I keep hearing from customers is they have requirements change in them every other day. And like the connectors move a little bit, the flex board shape moves a little bit, and you have to reroute. I had someone tell me they were in revision 54 of a flex connector that they had redesigned. Yeah.
Oh no.
And so all of a sudden it's like, man, sure, like it takes a few days to do it each time, but if you've done it 54 times, like you've spent a year on this flex
The
connector.
most expensive flex PCB of all time.
I mean, probably. So like, okay, can we get to the point where Quilter can pass a human design review on a flex connector? All of a sudden, if you're in that world where you're consistently redesigning because your environment is changing all the time and your connector placements are changing all the time, you've solved that problem. And it's far easier than solving a problem of this magnitude, right? But it's still a worthwhile commercial outcome.
It's also kind of a bit of a corner case where people either have expertise with flex PCBs or they don't. And if they don't, it's kind of like, ooh, what's it going to take to get me to ramp up into this realm and get, think about, how far it can bend and what sort of materials I can use and all that. But if you can solve that corner case, that alone is very valuable and powerful.
Yep, exactly, right? And so test boards are of a similar nature, right? Like, my background in SpaceX was specifically in radiation effects, right? We would take electronics, smack them with protons, smack them with heavy ions, and see what happens. And like all of those boards look really similar. You have some high density connectors on either side that go in and probe whatever the device under test is. You have some power circuitry to power it. You have some current sensors and whatnot. And then it's some device that you're testing in the middle. And you're basically, a lot of times we'd make a little daughter card that just swaps out for whatever device it is, right? Like that's effectively the same design at every aerospace company for all of the different radiation tests you do, and it still takes a week or two to design. If you automate it and it actually works, great, save a lot of time. So we look for like, what's the next thing we can build that's like that, that's repeatable and bounded and we can fully automate and get done with. Then once we conquer that, we go to the next thing and the next thing and the next thing. And hopefully we'll kind of hop our way to the servers over time.
So as you put together these puzzle pieces, I know I cut you off earlier, set me up for your vision for where are we in 10 years? What does this look like?
Yeah, I mean, in 10 years, like, I would hope that we start to see the benefits of this the way that the compiler made benefits for software, right? So let's put ourselves in that world where like the layout happens and we can trust it and we no longer review it. Like, what does that make possible, right? There's a bunch of obvious things that come from the analogy to the history of software, right? The first one is that you've abstracted that problem and made it much easier for many more people to do it, right? So a common complaint I hear is I'll have a firmware engineer who knows how to read and write schematics, doesn't really know the CAD tools and can't spin their own board. So they're sitting there with an eval kit and a bunch of breadboards trying to write code, and they're guessing whether they have a bug or a wire came loose, right? And they ask their electrical engineers to make a board, and there's never time for that. And so you're stuck with the eval kit and the breadboard, right? So, okay, like you've got people like that all of a sudden can just make boards very trivially and like not think about it. I think there's another set of companies other than Quilter, so I'll call out like CircuitMind, Celis, JIDEX, Autopile, Diode, these great companies that are looking at the schematic side of things, right? Like how do we kind of draw block diagrams or express in language or express in code some high level system intent and like fill in the BOM and fill in the interconnection. Okay, piece that with Quilter. Somebody actually just did that at a hackathon not last weekend as a basic demo. And you've got a like high level architecture diagram or even language prompt all the way through a working board. And so now people who aren't even electronics people can build boards, which is really interesting. For professionals, I think that the biggest thing that's going to happen is kind of the equivalent of CI/CD. Right. So in software, this cool thing happens where you've got potentially hundreds of people contributing to the same code base, and they make little changes here and there, and they submit a merge request, right? And then that merge request will run a whole bunch of tests. So if you broke somebody else's assumptions, you'll know. You introduce your own tests to protect your own functionality, right? And then you set it up for review. Everybody can see exactly what the change was, how the different metrics and performance was impacted. Everybody can agree and merge it in. So a compiler makes that possible for hardware, right? Like, so if your mechanical engineer comes and moves a connector, boom, the whole board gets relayed out. We create a diff, Everybody reviews, we check the physics report, see that nothing regressed, we accept the change. And all of a sudden, instead of that mechanical person like begging the electrical engineers to move the connector and being told no because it's too late, a story I've heard 1,000 times, they just do it and submit an MR. Right, and I think that will happen across all the inputs. Right, the inputs to the PCB are mechanical, it's firmware, it's parts choices, it's procurement, it's the mechanical constraints, it's thermal and constraints. All of these different things are something that ultimately ends up on the PCB designer's desk, something they have to accommodate. Right, but if people can independently push those constraints in and just rerun the system, all of a sudden hardware gets a lot easier. Right, so I think it's things like that are going to start to happen.
I love that. I'm really sad. We're running up on our time here, but we like to ask some quick questions, some kind of quick hit questions at the end of these things. Question number one for you, has there been any outputs from Quilter, any like layout design choices that felt very counterintuitive and maybe a designer would never have done it, but they end up working really well? And if so, what did that look like?
Yeah, I mean, I certainly say that doesn't happen often, right? We're not at the point where we're exceeding human capability. So if we're doing something weird, it's likely bad. Just to be very, very frank about it. But like one thing that we did do early on, which was kind of funny, is from first principles, I think we shouldn't be using octilinear traces everywhere. Like traces should just be curved and smooth everywhere, because that's in principle what makes the best waveguide, right? The least likely to reflect and the smoothest waveguide. And I first designed Quilter with just smooth traces everywhere, and I showed them to our first customer, and they were like, "What in the world is this? This is horrible."
Like, is this from the 70s? Yeah.
They even asked me, like, and this is like senior aerospace engineers who have flight hardware, like, is that even manufacturable? Like, what are you doing? Oh no, man! Like it's etching. It's I can draw Mickey Mouse for you. Like it's okay. Like it's gonna work. But it's such a gut reaction that we now post-process what we do to make it octilinear to like not flag that for people.
That is so funny. I mean, I've seen, I was like in Curious Mark's lab, and he has some like original Apollo hardware, and they have all those curved traces, and it feels very kind of, maybe that's the future. Maybe it's like a retro modern, return to curved traces.
It's in your RF equipment, right? Like your sophisticated VNA, if you take it apart, for sure those RF lines are nice and smooth. For sure.
Yeah. That's very carefully designed there for sure. Next question: if you had a magic wand and could change a rule of physics or of computing, what would you change, and what would that do for you?
Oh man, that's a good one. Okay, I'll give you a fun one. I think that I don't know what this fundamental property is, but it feels like there are algorithms that fundamentally just refuse to be parallelized. Like a good example is like something like Dijkstra. A planar graph search is kind of a very difficult thing to parallelize and actually get performance out of. And when you get stuck with these kinds of algorithms where you have to depend on like this sequential thing, then this sequential thing, then this sequential thing, you can't just use compute to brute force your way out of it. You have to kind of like fundamentally think of a different algorithm. And this happens in like training neural nets, right? The way you train a neural net is like very small stochastic gradient descent steps that have to happen in sequence, and you can't parallelize your way out of it. Graph search is an example. There's a bunch of these examples all over the place. And like those are the things that cause the most heartburn in terms of like, man, fundamental things about these algorithms that have to change for this to become possible. And so I don't know what mathematical property that is, but if there was a provable way to take a sequential algorithm and turn it parallel at a flip switch, which I'm pretty sure is impossible, but
yeah,
if it wasn't,
it sounds very like Shor's algorithm quantum computing adjacent. So maybe give it a little time and we'll have it. But that's a great answer. I've never heard anything close to that answer, and I love it. Last one. If you could go into space, you've worked on flight hardware. If you could be the flight hardware, would you do it?
Oh, 100%. Easy.
Yeah.
I believe one day I will. Like, I think that with all the work SpaceX is doing with Starship and all the other companies that are kicking ass out there, it will become cost effective to go to space, and I will for sure go. If I don't go in my lifetime, I'll be upset about it.
What a time to be alive, huh?
Yeah. Oh yeah.
Awesome. Well, this has been incredible. If someone wants to use Quilter, play around with it, where should they go and what should they do?
Yeah, come to our site, quilter.ai. From there, you can find your way into the free version and just play around with it, or come request a demo and talk to us. And of course, we're hiring all over the place. So if these problems sound fun to you, reach out and let's talk.
Awesome. Thank you so much. This is incredible.
Thank you, Daniel.
That was Quilter founder and CEO Sergiy Nesterenko, and this keynote was brought to you by Mouser Electronics. Delivering the newest electronic components for design, Mouser is your global authorized distributor for millions of components from over 1,200 leading manufacturer brands. Jumpstart your designs at Mouser.com. The All About Circuits Summit series happens each Wednesday in October, and sessions will also be available on demand. Today's live sessions are coming up, and they are all about PCB design and cover topics like electromechanical components, GaN tech, and integration with mechanical CAD tools. Each session you sign up for also gives you an entry into the giveaway, and make sure to check out the microsites from our partners to learn more about their topic. Thank you for joining me for today's keynote. I'm your host, Daniel Bogdanoff. I hope you have a great time in today's sessions, and I'll see you back here next Wednesday, where I'll be joined by Christian Ader of Congatech to talk all about embedded intelligence on the edge.